Hey, all you polar pre-calc pals of mine. I don't know. I tried. Hope you had a good break. It's time to get back into it, though. And if you're a little shaky on your polar coordinates, don't worry. You'll have plenty of a review right now when we do this. We're going to ease into it and do some full polar graphs. So we've got our polar coordinate plane here, and this equation, it has no r in it, it just has theta. Theta is a constant pi over 6. So let's just see what that ends up doing. This means theta is pi over 6 regardless of what r is. I don't think I'll need to plot this many points, but that means if r is -2, r is -1, 0, 1, 2, etc., theta is pi over 6. So let's start with the easy ones here. When r is 2, theta is pi over 6. Remember how you like to do that might be you like to go out 2 and then rotate an angle of pi over 6, which would put you right there. Or you might like to think of the angle of pi over 6 and then go out 2 along that line. Pi over 6, 1, or 1 comma pi over 6, because it is r comma theta that's given in, would be 1 pi over 6. 0 pi over 6. Remember, whenever r is 0, you're going to be right here at the pole, regardless of the angle. If your r is 0, you're right there. And that's actually a fairly important idea that comes up when we do the more complicated ones. When r is 0, you're at the pole. When r is -1 and theta is pi over 6. Remember these negative r values, you can either go left 1 and then go pi over 6 in the positive direction, which would put you right here. Or you can think of the pi over 6 line, but then going -1 along that line. And then -2 pi over 6 is going to put you right there. So I think you can see that regardless of what the r value is, it's just saying you're along the line of the pi over 6 line here. So you actually get a line out of it. That's talk about making an equation of a line complicated, but in polar form, that's what you look like. Theta is a constant. You get a line along that theta. What about when r is constant? Well, if you think about what you're saying, it's probably pretty logical, but if r is a constant of 5, and maybe we'll pick a few different theta values, 0, pi over 2, pi, 3 pi over 2, or anything you want. 5 comma 0, 2, 3, 4, 5. That's just 5 units straight to the right. 5 pi over 2, 1, 2, 3, 4, 5 would be 5 units straight up. 5 pi would be right here. And 5, 3 pi over 2 would be down here. Or really any angle you pick, if your radius is 5, you're staying right along this circle, and that's exactly what you get, is a circle. That's what a circle is. It's a set of all points that are equidistant from a given point. The given point being that center, and that distance is the radius. So if r is -3, you don't think of a circle as having a negative radius, so that might give you a little pause for concern, but r is fixed at -3. Again, if you pick whatever theta values you want, I'm just using the quadrantal ones because they're easy to work with. You should certainly use some other angles if you like. 0, -3, well, that just means you're going to be right there. And -3 pi over 2 would actually be the pi over 2, but 3 units down from there, or 3 to the left and pi over 2 from that moment. And -3 pi would put you right there, and -3 pi over 2 would put you right there. So really, the fact that it was a negative radius didn't really create any sort of exciting or super interesting graph. It's just a circle with a radius of 3. So that just is a directional kind of thing, but distance is always positive. You're just talking about a circle with a radius of 3. All right, well, let's just take this up a notch here with the back side, but hopefully the first side was pretty easy and just getting you back in touch with your polar coordinates. Now we've got r and theta in the same equation. So let's plug in some theta values and see what we get out for r. And you can plug in any theta values you want. The domain here is all real numbers, but let's stick with the quadrantals. If I want to pick anything in between, I can certainly go there. Maybe I'll leave a blank for something in between 0 and pi over 2, then pi, 3 pi over 2, 2 pi. Maybe I'll try a pi over 6. Okay, if you plug in 0 into this equation, sine of 0 is 0. Boom. Pi over 6. Sine of pi over 6 is 1/2. 1/2 of 6 is 3. Pi over 2. Sine of pi over 2 is 1. 1 times 6, 6. Plug in pi, 0. 3 pi over 2. Sine of 3 pi over 2 is -1, so we get -6. 2 pi, 0. Plot these points, and let's see what we got. 0, 0. Well, whenever r is 0, we're right there at the pole. R is 3. Theta is pi over 6. So that's the pi over 6 and an r value of 3. We're right there. 6 pi over 2. So 6 units out. Rotated an angle of pi over 2 would be 1, 2, 3, 4, 5, 6 units up. 0 pi. Well, r is 0. Guess where we are? We're right here. Doesn't matter what the angle is. R is -6. Theta is 3 pi over 2. So -6 and then 3 pi over 2 is really just going to put you right there. 0, 2 pi. Well, r is 0. You're right here again. I really didn't get that much out of that. So maybe try a couple other points here. How about pi over 3? How about some other things from maybe the second quadrant, like 2 pi over 3, 5 pi over 6. Some of these ones maybe I should have tried in between, but thought I could get away without it. Well, sine of pi over 3 is √3 over 2 times 6 will be 3 √3. 2 pi over 3, the sine of 2 pi over 3 is still positive √3 over 2, so you're still going to get 3 √3. 5 pi over 6, sine of 5 pi over 6 is still positive 1/2, quadrant 2, sine is positive, and so you get 3. So it's nice to see these points. These points really occurred all between 0 and pi. You know, this one occurred before pi over 2, 6. But let's see what we get here. 3 √3 pi over 3. So that would be along the pi over 3 line, but a radius of 3 √3. 3 √3 is the equivalent of √27, which is a little bit more than 5. So 1, 2, 3, 4, 5, and a little bit more than that would put you right about there. 2 pi over 3, 3 √3, will put you at that same radius, but along the 2 pi over 3 line, which is right there. 5 pi over 6 and an r value of 3 will put you along the 5 pi over 6 line, but at a radius of 3. Now you might start to see what you get out of this, that you really just get another circle, but it's not centered around the origin. And so you get that. And one way to think about this that we're going to look at maybe with some tougher ones is to think about our connection to our sinusoidal graphs. I think this is, if nothing else, this is a nice way to review that idea. That think about the equation of y equals 6 sine of x. The same exact equation, but instead of r and theta, y and x. That equation is the sinusoidal graph with an amplitude of 6 and a period of 2 pi. And if you'll remember, it's been a while maybe, but positive sine starts right here at 0, 0, and then at pi over 2, sine is positive 1, so it goes up, and you get that one complete crest between 0 and pi, and then between pi and 2 pi, it dips down. You get this complete trough with an amplitude of 6. But now in polar form, all you're measuring here is the distance away from this initial point. So you can kind of see that this right here, this portion, when you go from there to there, as your angle increases from 0 to pi over 2, and your radius, instead of your y value, think of it as your radius, your outcome, your output. As your theta increases from 0 to pi over 2, your radius increases from 0 to 6. So it's right here. It's kind of as you sweep between 0 and pi over 2, think about sort of as my angle is increasing, as I'm getting closer to pi over 2, the radius here from 0, 0 is increasing until it's at 6. But then after that point, then that distance starts to decrease back down. My radius value starts to decrease, and it's being pulled back towards this point right here. And so, and then here in the negative direction, it's just getting reeled out. That distance is 6. It's negative 6, it's below, but that's still just a distance of 6. So it's just reeling this back out. And if you like, you can see this play out on the graphing calculator. The Desmos is great for this too. Obviously, Desmos draws nicer graphs than anything. But one thing that actually is nice about the TI-84, some of the other graphing calculators, is if you, first of all, you have to change the mode, not from function, not from parametric, but to polar right there. And then when you go to y equals, it's all in terms of r and theta. I'm in radian mode, which is what I want it to be. And you hit graph, and you see it graphs it in that order. You see it sweeping as 0 to 2 pi. You see it go in that order. And if you're wondering, that doesn't really look like a circle, it's kind of squashed. It's because this scale is negative 10 to 10 on the x-axis and negative 10 to 10 on the y-axis. But this physical distance on your calculator is shorter than this, so it's stretched more in this direction. One way you can fix that is you can go to zoom, and there's that feature right there, 5, which is zoom square, and that will adjust it so it's the same exact distance in each direction. So there's a nice circle around the y-axis going right down the middle. And you can push the trace around on this, and you can see as theta increases, you can see the actual rectangular coordinates at that spot. And so that's right there at 1.57, and that, of course, is pi over 2, 3.14 divided by 2. You're right here at 0.6. Cool, right? You can type in, remember, you can type in like 5 pi over 6. You can type in the theta values, and it'll move it to that exact spot. So kind of a cool way to check your graphs. But let's get back to this here. If r is 4 cosine of theta, again, I'll plug in some values, but I'm going to leave a little space here in between these. Pi over 2, pi, 3 pi over 2, 2 pi. Maybe I'll need to plug in values in between each one of those. And with cosine, I like to plug in pi over 3, because that's where you'll get out 1/2, negative 1/2, and things that are easy to work with. So I'll try 2 pi over 3, then I'll do 4 pi over 3, and then I'll do 5 pi over 3. You can always do more if you like. If I plug in 0, cosine of 0 is 1, so r will actually be 4. Pi over 3, cosine of that is 1/2. 4 times 1/2 is 2. Pi over 2, all the cosines at pi over 2 are 0. 2 pi over 3, be careful, that's quadrant 2. Cosine is negative 1/2 times 4, which is negative 2. Pi, cosine of pi is negative 1, so we get negative 4. 4 pi over 3, cosine is negative 1/2, so negative 2. 3 pi over 2, that's 0. 5 pi over 3. Now you're back to quadrant 4 where cosine is positive. So that's positive 1/2, so we get positive 2. And 2 pi, we're back to being 1, so 4. And plot these points. 4, 0, r is 4, theta is 0, 1, 2, 3, 4. We're right here on the x-axis. 2 pi over 3, so 2 pi over 3. 0 pi over 2. R is 0, you're at the pole. Negative 2, 2 pi over 3. So 2 pi over 3 will put you right here, but then r is negative 2, so 2 units behind. Pi, but then negative 4 puts you 4 units behind backwards, so that will put you right there actually. Negative 2, 4 pi over 3, so 4 pi over 3, but negative 2 puts you right back on that point, and you're starting to get the idea. We're just going back and forth between these points. You've actually got yourself another circle. You could plug in more points if you want to see it take shape, plug in some pi over 4s, some pi over 6s, and get those values. But you'll start to trust these kinds of things, that you've got another circle here. And to compare it to the sinusoidal graph of y equals 4 cosine of x, that would again have a period of 2 pi. An amplitude of 4 in this case. So as high as 4, low as negative 4. The midline is 0. We haven't shifted it up or down. And with positive cosine, that starts at the top of that, at the crest, at the top of the crest, the top of the wave. So 0, 4. And then at pi over 2, you're down to 0. And then pi, you're down here. And then 3 pi over 2, 0. And there was your positive cosine graph. If you want to think of that correlation between what you drew and what you're showing here, it's as your theta increases, you're moving in a circular motion, and when theta is 0, r is 4. So that's kind of where we started. And as theta increases, r is decreasing down to 0. So as you were going out between 0 and pi over 2, your r value was decreasing and sort of getting reeled back towards that pole. That portion right there corresponds to this portion along here. As you rotated, your r value decreased down to 0. But then you continued rotating in a circular fashion, and your r value increased again. It reeled out to being negative 4. So it went from here to there, and then it got reeled back towards 0, and then got reeled out again, and so on and so forth if I keep going. So you've got a circle. Here's some other little properties to note, that if it's sine of theta, r equals 6 sine of theta, notice we got a circle with a radius of 3, not a radius of 6. The diameter was 6. And look, it's symmetric with the y-axis. With the cosine, the diameter was 4, but this is symmetric with the x-axis. And that's not a coincidence if you think cosine is always associated with the x-coordinate and the x-axis, and the sine is always with the y-axis and the y-coordinates. So you'll start to pick up on these things. Negative 3 cosine, you might start to make some shortcuts and say it's a diameter of 3 cosine. That's going to be a circle on the x-axis. But let's just plug in a couple points here. And once you get the hang, you might not have to plug in many points at all. Maybe just a few. If you plug in 0, cosine of 0 is 1, so we get negative 3. Pi over 2, 0. Pi, negative 1 times negative 3 is 3. Let's see if we got enough just from those points. Theta is 0 when r is negative 3, so doesn't matter. Negative 3, we're right here, and then theta is 0. So r is 0 when theta is pi over 2. R is 0, you're right here at the pole. r is 3, but it's pi. Well, that puts you right here at that point. You've got yourself a circle with a diameter of 3, and it's centered around the x-axis, but notice it's on the left side, and that's what that negative did. If you want to see the sinusoidal, you're going to have a negative cosine with an amplitude of 3. So this starts at the bottom, and that's what we started with right there. That was our first point. And then as we moved from 0 to pi over 2, this we rotated in that fashion, but our r value got reeled back towards the being 0. And then from here to there, we get reeled out. Our r value increased to right here, corresponded with that, our maximum value, the maximum distance away, and then we got pulled back towards 0, and then reeled back out, and so on and so forth in that circular fashion. So there you go. These graphs aren't too complicated yet, but think about these connections besides just plugging in points for where we go with it in the next few days. Check with Desmos, check with the graphing calculator, and of course check with me if you got any questions. I'm here to help, so let me know. Have fun, guys.